What's up, YouTubers? Welcome back to Structure Free Learning, and in this video we're going to do another moment area method example of a simply supported beam with a uniformly distributed load with a length of L. I want to find the slope at A and the deflection at midspan. And one of the things that I want to do here is that I want to make sure that we all understand that when I define deflections, I'm using this coordinate system here. This is my plus x and here's my plus v, so that point A is my origin. Now in this problem, I'm going to use the moment area method. So one of the first things that we need to do is come up with the moment diagram and then the curvature diagram. And so I'm going to assume that you can calculate reactions and shears and moment diagrams here. So the moment diagram will look like this. So the moment diagram is parabolic. It has a max value right here, where the slope of the moment diagram is 0, is WL squared over 8. And this would represent my moment diagram. To get the curvature diagram, because the flexural rigidity is constant, I can just divide everything by EI. And so the curvature diagram here is this right here. The first thing I'm going to tackle is the slope at A. And so when I do that, I want to draw a qualitative deflected shape using the moment diagram. And because I know I have this positive moment, my beam is basically a happy face, if you will. And so if I draw my deflected shape, here is my undeflected shape, or my original structure. And with the loading applied to it, this is what my deflected shape will look like. Now here's a good time to kind of think about what the structure is doing, or what the deflected shape is doing. And it's important here because we have a symmetric loading and a symmetric structure. And when I say symmetric structure, I mean that we have symmetric boundary conditions, or the reactions here. I would only have, based on the loading, vertical reactions here. The horizontal at A would be 0. So I have a symmetric structure and a symmetric loading. And so what I know is that my deflected shape is also going to be symmetric. And what's more is that I know that my maximum deflection occurs at the midspan, and the slope of the deflected shape here is 0 at this point, at the midspan. And when you apply the moment area method, knowing where the slope is 0 or the deflection is 0 or where the deflection is maximum is really important in setting up a reference, because the slope calculation and even the displacement calculation using moment area methods are all relative. Now that I have a sense of the deflected shape, I can go ahead and try to calculate the slope at A. And because I know there's a point along the length of the beam where my slope is 0, I can use that as one point. And so at midspan, I'm going to draw the tangent line to the midspan here. And then I can draw the slope at A, or the tangent line to point A. And what I know is that this angle right here is the change in slope from point A to the midspan. So now I can apply my first moment area theorem is equal to the integral from 0 to midspan here, which is L over 2. So this point is 0, this point is L over 2 on my x-axis. So I'm going from 0 to L over 2 of the area of the curvature diagram, dx. So to solve this integral, you can actually come up with a moment function here, come up with a curvature function, and then just integrate from 0 to L over 2. That's one way to go about it. Another way is to utilize tools that are available in your textbook and on the internet. And I found on the internet, I think it was like engineering.com, right? The centroid and area properties of various geometric shapes. And for a parabola, or half a parabola, where the slope at one point or one end is 0, what I found is that the area, this area, is equal to 2/3, and let me call this the base, and this distance, the height, 2/3 BH is the area. The centroid, which I will put right here, C, is 3/8 from the fat side, if you will. This would be 3/8. And this distance from the skinny side is 5/8 B. And then in the vertical, if we needed that, this would be, this distance is 2/5 H, and this distance is 3/5. So now all I'm doing right now is just calculating this right here. And that area is equal to 2/3 times the base, which is L over 2, times the height, which is WL squared over 8EI. And this gives me WL cubed over 24EI. And notice I got a positive result here. And what that means is that the angle going from the tangent line at A to the tangent line at B is positive. That means my angle is going like that. It's rotating counterclockwise. But when I look at it in terms of my coordinate system that I established for this beam, this V and the X, the slope of point A is like this, is downwards, if you will, and that is a negative slope in this Vx coordinate system. So the actual slope of point A is equal to minus WL cubed over 24EI. Alright, that's one. Now the next thing I want to do is calculate this vertical deflection at the midspan. And so in order to do that, I need my moment diagram. I want my qualitative deflected shape again, and this geometry information. So let me just get rid of this other stuff over here. When I take a closer look at this deflected shape, or the qualitative deflected shape, what I notice is that I have the tangent line at the midspan, and here this tangent line at point A. And theorem number 2 says that the vertical deviation from the tangent line at midspan to point A can be calculated. This blue distance right here is TA mid. This can be calculated by the first moment of area from A to the midspan, which is x bar A from 0 to L over 2 m over EI times dx. Again, you could do the integral and blah 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 blah, but here we've got the geometric properties of a parabola, and there's no need to get all crazy and do that. We've already calculated that this area from the first part, when we calculate the slope, is WL cubed over 24EI. The distance, the arm, is the distance from point A to the centroid of the area, which is right about here. Bam. And this distance, according to our chart, is this 5/8 B. And B is the same as L over 2. So this is 5/8 times L over 2. That is this distance, which represents x bar A. And so now if I go ahead and I substitute these values that I know, let's go with red for the centroidal distance, 5/8 times L over 2. And then the area we said was WL cubed over 24EI. And I do some number crunching, and this thing will get me 5 over 384 WL to the 4th over EI. And notice this, we get a positive result, which means that that point A is above the tangent line at midspan. Okay, so we have to go from here, the tangent line at midspan, we have to go upwards to get to point A, and then we get the positive result. But according to our coordinate system for the beam, this V and the X that we established, a deflection or a point on the beam that's below the x-axis is considered negative. And so in this case, the deflection at midspan is equal to minus 5 over 384 WL to the 4th over EI. Bam! And that's it. That's how to get it done. So hopefully that was enjoyable and a relatively simple example problem with a simply supported beam. We'll do something else, another example that doesn't have a symmetric structure and a symmetric loading. Alright, take it easy. See ya.